Unit Operation Classroom. Today we are discussing activation energy under strong pore diffusion regime. My name is Shekhar Bhattacharjee. An irreversible chemical reaction occurs on a porous catalyst. So let's assume this is a porous catalyst and it's immersed in a bulk gas of the reactants, of course, products, everything is here. All the pores are of same size. In strong pore diffusion regime, the observed activation energy is given. Let's see what happens from the. This is an external diffusion from the bulk gas. The let's say the reactants diffuse to the catalyst surface here, and then after that it enters the reactants enter the catalyst pores. There's a highly connected interconnected catalyst pores, and there is of course diffusional resistance to travel inside the catalyst pores. But once it reaches a certain active site, then of course the intrinsic reaction occurs, and the reactants are converted to products, and then the products follow the reverse procedure, come back to the diffusion limitation inside the pores, and then go out in the bulk gas. Now, it says that the observed reaction rate, activation energy. Why observed? Basically, because the observed reaction rate is a summation of external diffusion, of course, and then the diffusion inside the catalyst pores, and then, of course, the intrinsic reaction at the active site. Now, this is normally very fast, so this really does not count. So basically, observed reaction rate is mainly influenced by the diffusional resistance inside the catalyst pores and the actual reaction rate. It's a series process. Okay. So the observed reaction rate is the activation energy. Activation energy, observed reaction rate. So any reaction rate can be in some kind of a pre-exponential factor constant, exponential negative of the activation energy divided by RT, right? So one is the observed reaction rate, observed, and one of course is the actual reaction rate. Let's call that ER, and of course another is the activation energy for diffusion inside the process. This diffusion process inside the process. The activation energy for diffusion is 10 kilojoule per mole. Normally, this is very small, somewhere between 10 to 15 kilojoule per mole. Whereas the actual reaction rate, so this is in the very high range, approximately 100 to 120 kilojoule per mole. 100 to 120 kilojoule per mole. Assuming Arrhenius temperature dependence for both reaction rate and diffusion, which one of the following is the true activation energy, which is probably the activation energy of the actual the intrinsic kinetics? Before we go into this one, let's quickly go to page 390 of 11 spiel. And here you can see under this strong pore diffusion region, the E observed is actually the E true, that the true reaction activation energy for the true reaction kinetics, and the activation energy of the diffusion and divided by 2 is just the average. Since this is very small, as I said, compared to this true, normally we can neglect that, and normally E observed is approximately equal to E true over 2. Okay. Now, let us try to see a little bit of the physics behind this equation. We can say the observed reaction rate, that means the overall reaction rate, is eta Kc, where K is, of course, the first order reaction rate constant, and C is the concentration inside the catalyst pores, and eta is, of course, the effectiveness factor. We know in strong pore diffusion regime, you can go again to Levin's field, eta is proportional to 1 over 5, where phi is the Thiele modulus, which is defined by this one. So eta k, which is right here, eta k, we can say that is proportional to, just take the inverse of that. So this one times this one, so it is KDE. So absorbed rate is proportional to square root of KD multiplied by C, which is the concentration inside the pore. If we assume Arrhenius type of temperature dependency for both K and that means true kinetics and diffusion kinetics, a diffusion process, then we can just say this is equal to this, which is this one right here, and for D we can write this one right here. Just a little bit of mathematics. We take this negative and we just add up these two because both of them are on the e to the negative sign. So we can just say, and we can take the square root out and put 2 here. So exponential of negative of ER plus EA divided by 2 RT. So if I compare this with the standard Arrhenius kinetics, we know this normally is constantly constant exponential minus of E observed divided by RT, where of course E observed is going to be equal to ER plus E divided by 2. Right, so that's what it is right here. Now, according to the problem, E observed is given as 120, which is the observed activation energy is 120 kilojoule per mole, and for the diffusion activation energy is 10. So the true kinetics, activation energy for the true kinetics 230 kilojoule per mole, which is of course this one. And if we take E true divided by 2, so E true is going to be approximately equal to E observed multiplied by 2, and which is of course equal to 1. E observed is 120, is 120, so 120 multiplied 2 would have been 240. But if you do the exact calculation, we found a D. So D is of course the correct option. Okay. All right. Having said that, also I just wanted to say that in spite of all these video concepts and everything, read a good textbooks to develop your own concepts. Let us look into. You can stop the video if you want to, but I'm going to next discuss a process industry application of this particular problem. Let's look at the ammonia synthesis, one of the very highly important industrial process, Haber-Bosch process. This, of course, we know as a reaction. Now, under the conditions of high temperature and pressure, the high temperature and pressures are utilized for this Haber-Bosch process. Under these conditions, we have a very fast intrinsic kinetics. Okay, but the pore diffusion is much slower compared to this one. So this inhibits this, lowers down the observed overall reaction kinetics. So measured activation energy is much lower than the intrinsic. So this is a typical ammonia catalyst, iron pellets. Typical value of ER, true kinetics, we say around in the range of 90 to 120 kilojoule per mole. Typical activation energy for the diffusion process is around 5 to kilojoule per mole, and the E observed is in the range of 40 to 70 kilojoule per mole. So there you can see that the observed kinetics is slower than the true kinetics. So that is not because of the inefficient design of the catalyst. That's a pore diffusion. So we need to, if we want to make it higher, if you want to make it faster, then the design of the catalyst should be stressed upon. Okay, so under this situation, because of diffusion, as you can see, first there will be fast surface reaction, means where it does not have to go to the trouble of going inside the pores, and there's a strong pore diffusion, and the pellet core remains underutilized. Another typical example we can see is the hydrocracking or hydrodesulfurization process. Very quickly, where heavy hydrocarbon, where vacuum gas oil or the atmospheric gas oil or coker gas oil, these are normally very heavy fractions from vacuum distillation columns. These are high molecular weight, contain sulfur, nitrogen, and they have aromatics. And normally, these are low value without upgradation. So how do we do the upgradation? We do the hydrocracking and hydrodesulfurization, and these are the typical temperature range, pressure range, and we use different types of catalyst here. So what are the products? The desired products are LPG, CT2C4, which is used for cooking gas, petrochemical feed, and naphtha. In this particular carbon range, petrochemicals, gasoline blending, they are used. Kerosene, C8 to C16 range, which is used used for aviation turbine fuel, and the diesel, they try to maximize in the hydrocracking process. This is the carbon range for the transport fuel, which we all know. And of course, at the same time, sulfur gets converted to H2S and nitrogen gets converted to ammonia, and the aromatics are hydrogenated. So, what is the relevance to this particular problem? So, when we design the catalyst, we must remember this large molecules. So, these are very large molecules. They slowly, very slowly diffuse. They tend to very slowly diffuse with the catalyst course. There's a strong diffusion limitation. So, these catalysts have to be very carefully designed, and the reactors have to be very carefully designed for such a complicated process where the catalyst, where the reactants encounter a very strong pore diffusion. Finally, as I said, for this particular problem, D is the correct option.